Hello, future Lexi. Welcome to TP5 Homework 1 Recap. I'm going to go over the questions, read out the questions, which are going to be quite lengthy because of the style of the homework, and then go through the answers, and then just go for a recap at the end. Sorry about the setup. I wasn't bothered to do the whole screen recording thing. Just deal with it, honestly. Anyway, exercise 1. For a classical ideal gas of volume V, the pressure P depends on the particle number N and the absolute temperature T via the thermonuclear state equation PV equals NKBT with Boltzmann's constant KB setting the temperature scale. Sounds kind of confusing. He's just saying that PV equals NKBT is a thing, honestly. Following their early Nobel laureates, chemists long adhered to an old Leipzig tradition and expressed the same law in molar units as PV equals RT, or PV equals nRT, but this is in molar units, so it's, yeah. Sadistically, they define the mole as the amount of matter that would weigh 12 grams for the isotope carbon-12, which they tortured generations of physicists and underage kids until, to their great dismay, it was eventually redefined as the amount of matter containing the Avogadro's number amount of molecules in the year 2019. He's just saying what the definition of a mole is, whatever. Question 1. Determine the exact molar constant gas R and its approximate value in modern unit convention. He gave us PV equals NKBT. He gave us PV equals RT. That just means R is equal to NKB, or actually NR is equal to NKBT, because we know it's this. We know PV equals nRT. You do that, R is equal to N over NKB. Big N here is the number of molecules, small n here is the number of moles. Number of molecules divided by number of moles, kind of by definition, is Avogadro's number, the amount of molecules in 1 mole. And we have both of these numbers, and A and KB, given in the question. Plug them into a calculator, you get R. R is also a value you can just find plentiful online. Question 2, what is the volume of a mole of an ideal gas at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius? What's the volume? You get PV equals, well, we used RT here. V is equal to RT over P. Sub everything in, you get an answer. Determine the values of the thermal expansion and stress coefficients alpha and beta given by this, respectively, for an ideal gas, where delta T is equal to T minus T naught. This, I mean, the concept of it isn't really needed for the question. The question is just like basic algebra, but it's just telling you volume with respect, changing with respect to temperature, which is scaled by some thermal expansion coefficient and at a constant P. Same with pressure as a function of temperature being scaled by some beta, the constant V. What you do is, so let's start with the VT. It's the exact same process for both of them. Let's start with this VT1. P is equal to V. PV is equal to RT. V is equal to RT over P. You sub that in for V and V here. For this one, R and T and P are all like R is a constant, so you can cross that off both. Here we're this one is the current temperature, so it's T. This one is the initial temperature, so it's T naught, and we're told that it's a constant P, so it's P naught for both. You can cancel out R and P naught. You're left with this. We know that delta T is just T minus T naught. Sub that in. Do algebra. You get alpha is equal to 1 over T naught, and you do the same thing for beta. It's whatever. Now, question 2. The heat capacity for a fixed amount of material is defined as this. C is equal to delta Q over dt, I guess, where X denotes a variable held constant during the measurement, example, pressure or volume. Given the incremental mechanical work has the form PDV for the material, write out the first law for its internal energy to demonstrate that this, and evaluate it for an ideal gas. So what he's saying here, given that incremental mechanical work has the form PDV, it's just dW, or sorry, I think it should be this dW is equal to P dV. This is what he wants. I have here. And its first law for an internal energy is this one here. Q is equal to delta U plus W. Now, if we look at this original heat capacity equation he gave us, you could see this dQ. You could see a Q here. Make it delta Q. you make a delta Q, delta, delta. You have a delta W, which is what he was given, the dW is equal to PdV. Sub that in. It's a bunch of subbing in, and then you come here. This is a total differential form of du. You can find this in a textbook. It's maths. You probably have seen this before. You sub that in for this du. You organize everything, and then you have this general equation for your heat capacity. So C is equal to, something. Let's say C is equal to, earlier, how it's like Cx is equal to x, where x is some variable held constant. We want CV and CP. Let's see V. Let's see V. A CV, a resume, a CD. What am I saying? I don't care. So CV, V, if V is held constant, and we look at this term over here, then this is a constant. Derivative of a constant is 0. This whole term goes to 0. You're left with just this CV, or here, CV is equal to this first term. Now, let's go back here. Wait for it to disappear. CP, then, is equal to this thing, P, right? Or, well, I guess it would be this here, P. So now we sub in. Also, there are like little discrepancies in this thing that I don't really know the answer to. I honestly don't care. You sub in this thing. You sub it in for CV because we just got that it was CV. Bring CV over to the other side, and now you have literally exactly what he asked for in the question. For part B, I don't know. Sorry, I genuinely don't know. We tried and we got somewhere, but we didn't get to the answer, and I don't care. There's a bonus on total differentials, which is what I was talking about up here with the du, with the total energy. Internal energy, I should say. Check whether the following are closed or even total / exact, i.e. globally closed differentials, du, and find u accordingly. Here, I actually didn't find u, but to find u, you literally just look at here. Like, okay, this is question 1, right? This is equal to du. To find u, you do integral, and these are pretty simple integrals. This is u, and this is going to be the integral of y minus x squared dx. You can do that. And for this one, if it's, now I'm not fully sure, but homework partner did something and it looks right, so I'm just gonna trust her. If we're asked to find out if it's closed or exact. Where I'm just saying, if it's exact, then it follows this, and if it doesn't, then it's closed. And what this is so let me actually just write it down. Du takes the form, which one did I do? Okay, n dx plus m dy. This is a first order total differential. So as we can see here, this is the n and this is the m. So if, due to the fact that it's a well-behaved continuous thing, and I'll go over more later actually, you just have to know that this works. So you find the x derivative, the y derivative of the first part, x derivative of the second part. If they're the same, it's exact. If not the same, it's closed, i.e. not it's not exact as like it's globally closed, and just closed means it's just locally closed. For the first one, you could see that 1 equals 1, it's exact. This one is not, and this one, it's just differentiation in algebra, man. Let's just go up to the recap. The question 1 is just formula, For question 2, PV equals NKBT with big N, PV equals nRT with small n, and then number of molecules divided by number of moles is Avogadro's number. Wow. Heat capacity, Cx is equal to delta Q over dt, is the heat change per temperature increment increase to not increased variable x. For example, how much heat you have to put into something to raise its temperature by 1 degree or whatever, to not change pressure or volume and stuff like that. Thermodynamics first law, I just wrote it down, I didn't really read into it, I'll read into it more later. Q is equal to delta U plus W, work, and this is basically like how much work is needed to expand a compressed system, because it's pressure and little increments of volume, the pressure to volume kind of thing. you get it. What is the difference between all of these d's and deltas? This delta is just pure difference. Nothing infinitesimal about it. This is just an infinitesimal, element, tiny little dA, dx, dy, whatever you want. This is partial derivative, but this miniature delta, what is it called? Lowercase delta, it's used to represent an infinitesimal element of a non-state function. A state function is independent of the path taken and depends only on the current state of the system, while a path or non-state function depends on the path. A state function is like the internal energy, the pressure, the temperature, or the volume, and a path function is like the heat or the work. UPTV. Question 2 part 2. I don't know. And the bonus question, I forgot, excuse me, sorry. The reason why this is true is because the equation is well behaved and continuous versus partials, which means that it doesn't matter the order in which you do the partial differentiation. If you have a function and you do the x differential, they should be partials, actually. I'm so sorry. If you do this and you do the x derivative, you find the x derivative and then the y, or the y and then the x, then it shouldn't matter. And up here, remember we have this thing? This is the form of it, actually, because of the chain rule. So we've actually defined this to, actually I have it reversed on it earlier, but you get it. This part is m and this part is n. So that means in here it's m and in here it's n. So, which is literally just what we have up here. So yeah, that's that now, isn't it? Okay, goodbye.